First step is isolate the whole member, the whole body. So free body diagram looks something like that. And external loads, you have the 10,000. And then all the pins are internal. So what load do you have here at C? What kind of load? Yep, I'll call that FC. And what do you have at D? Vertical. Newton's second law says 0, 10,000 plus FCX, FCY plus 0 FD is equal to zeros. And the rotational equation, I'll do that about C, about the origin. Says this moment arm is 0.5, so we have, and that's clockwise, so we have negative 5,000. And then no moment due to FC. This distance is 1, so we have a counterclockwise moment of FD equal to 0.
Is that 5,000 or 500?
5,000 because this is 10,000. So everything after that is wrong. Okay, so FD is equal to 5,000. And then FC is equal to 0. What do we got? 15,000. Negative 15,000. Okay. And then let's go on to member 1. We have the negative 15,000 here, right? There's a bunch of ways you could write that, like this. You could also write it as a vector of 0, negative 15,000. Then what force do you have here at joint A? This is where it connects with member 2. So what force do you have there? We're looking at 1, so it's on 1 by 2. And then up here, that's where it connects with 3. So that's F13. And I have sort of a general question. We're going to see in this problem that we never have to deal with that issue of like what member the pin is connected to. You know how like in the problem set that you just turned in today, you always had to worry about like, okay, the ball in the joint is connected to the lowest numbered member. What joints are touching, or what members are touching what? And you have to deal with that in 2D problems sometimes. You're not going to have to in this one. So what's the reason for that? What's going on here that's not going on in the problem set so that issue goes away?
There's no more than two.
Yeah, that's exactly it. Yeah, every joint has just 2 members at it, okay? That issue of like having to figure out decide what the pin is going to be a part of is an issue that only comes up when you have 3 or more members at a joint, okay? So that's something I think to keep in mind. Okay, so Newton's second law. we have 0, negative 15,000 plus f12x, f12y plus f13x, f13y is equal to zeros. And the rotational equation, I'll compute the moments again right about this point, C, which is also the origin. So there's no moment produced by this downward force. What moment's produced by F12 about this point? Yep. And the y component doesn't contribute at all. And so this is what I was saying before about how if you can get by treating only vertical and horizontal members, it simplifies things a little, because that diagonal member, you'd have to deal with x and y components for all the forces. And this one, yep, moment arm of 1, F13x is equal to 0. And so we get our first 3 equations for our big final system of equations. F12x plus F13x is equal to 0. F12y plus F13y is equal to 15,000. And negative 0.5 F12x minus F13x is equal to 0. And so right now for variables, we have F12 x and y, F13 x and y, and that's it. So 4 variables, 3 equations, so we can't solve for anything yet. Any questions about that, member? And then let's go on to member 2. What loads are acting at this point? It's that upward force of 10,000. How about at the middle point? Yep. And here? Yep, F23. So Newton's second law says 0, 10,000 plus F21x and y plus F23 x and y is equal to zeros. And this time I'll compute the moments about, let's see, what's that point? I'll do it about that midpoint, A. And of course, like always, you could do this with the table if you wanted. So we have a moment arm of 0.5 here. It's a clockwise moment, so we have negative 5,000. And then a moment arm of 0.5 here. The y component will produce a counterclockwise moment. So 0.5 F23y. And so equations 4, 5, and 6 are, okay, now this is where I'm gonna like reduce my variables. So we have to look back at our list of variables that we already have and see what we can use Newton's third law to replace. So any F2 1s we're going to replace with F1 2s. This doesn't have any 3 1s in it, so that's the only thing we're going to replace is the 2 1s we're going to replace with -1 2s. So negative F1 2x plus F2 3x is equal to 0. Then negative F1 2y plus F2 3y is equal to negative 10,000. And then 6.5 F2 3y is equal to 5,000. And your variables, we still have the same ones we had before, 1, 2, and 1, 3. And the only thing we've added is the force vector F2 3. Okay. So now we have 6 variables, 6 equations, so we can solve this system now. Anybody get that same set of equations I got? Yeah, if you use different about points, they're different. And so if you solve that system, you get let's see. I guess I didn't write down what the force vectors are, but I wrote it down in terms of the external forces. So on member 1, you have a 5,000 Newton force acting down. You have a 20,000 Newton force up and a 15,000 Newton force down. Okay. The horizontal member, you have 10,000 up, 20,000 down, and 10,000 up. And the diagonal member, you have 5,000 up, 10,000 down, and 5,000 up. And so, of course, because of Newton's third law, like this is the member, this is the force F1 would be 0, 20,000, right? So the force F2 has to be 0, negative 20,000. And so you see that at every one of these points. You have a force one direction on one member, equal and opposite on the other member. Here, the negative 5,000, positive 5,000. Here, the 10,000 up, 10,000 down. Okay, those are the pairs. All right. So the next step, now we have all the external loads on those members. So now we're going to rotate those members and deal with the internal loads. So let's start with member 1. So right now, everything is in terms of a, our vectors are all in a coordinate system oriented like this. For each one of these members, we want to express these vectors in coordinate systems that are rotated along the length, okay? 1 and 2 are pretty easy. Member 3 is, not, it can get a lot more complicated than that, but member 3 takes a little more thinking to get those vectors right, I guess. So let's start with member 1. So if we are looking at it this way, with our coordinate system, oriented like this, and really, since I didn't even write it as vectors, there's not, you can just sort of eyeball this. So this rotates to 5,000, 20,000 this way, and then 15,000 this way. And actually, let's see. Well, let's do it this way. So, what if those had been treated as vectors? Like, what if instead we treated this as -0, -5,000, here 0, 20,000, and here 0, -15,000. How would we use a rotation matrix to express these in a rotated coordinate system, or to express them in this coordinate system? Yeah. So, but I guess I'm thinking that's right. But yeah, what rotation matrix would we use? What angle would we want here? Okay, so this is tricky. When you're first doing it, we're sort of rotating the member. We are rotating the member positive 90 degrees, but that's the equivalent of rotating the coordinate system negative 90 degrees. You see that? Because we're trying to go from a coordinate system like this to a coordinate system like this. Okay? So you'd multiply each of these by cosine -90, sine -90, negative sine -90, cosine -90. And it would just give you the vectors that would tell this story. For cases this simple, it doesn't matter much, but you can imagine things get messier, at least by hand, if you have something that has X and Y components, and you kind of would have to break it up into components and whatever. It's just easier to multiply that matrix. Okay. So how many important points are there in this member? 3 important points, 2 cuts. Okay. So work together now and do those 2 cuts and come up with the tension, shear force, and bending moment diagrams for this member.